Hi, my name is Madeline and I'm part of the residential program.
I'm Sophia Harvey, and I'm part of the online program.
I am Myeongkwon and for the residential program.
So this is the problem. Shown below from left to right are the graphs of r equals sine of 4 theta over 3 and r equals sine of 6 theta over 5, where every other adjacent region starting from the outside is shaded black. And we were supposed to find the total shaded region for any such graph of r equals sine of k plus 1 theta over k, where k is an odd positive integer and theta ranges from 0 to 2k pi.
We can integrate by dividing the graphs into sectors. For example, below is a sector for k equals 3. And putting this all together, here's a sum of the integrals that gives the shaded area of one sector for k equals 3, which equals pi over 32. And since the shaded area of the half sector is pi over 32, and there are 16 half petals for k equals 3, the area of the whole shaded region is pi over 2. And using the similar approach for k equals 1, 5, and 7, we find that the area of the shaded region for all four values of k is pi over 2. Our claim is that the area of the shaded region for any odd positive integer of k is pi over 2.
Due to the symmetry of the polar function, adding and subtracting the same section on a different petal yields the same answer. So we can replace the complex integral sum from earlier with the following integral sum, which uses much simpler angles. The result of the integral sum is pi over 2. So our claim is that the general formula of the shaded area of the half petal for any odd positive integer k is the following. And we'll multiply this formula by the total number of petals, 4 times k plus 1, to get the area of the shaded regions for the entire function.
Okay, so instead of using an alternating series to evaluate the integral, we're going to use the following steps. First, we're going to add the whole region together by integrating from 0 to k pi over 2k plus 1. And then we're going to subtract the white regions once to account for the extra addition. And then we're going to subtract the white space a second time to find only the black area. So this is going to be the whole sum minus twice the sum of the negative integrals equals pi over 2. So here it's represented mathematically, and when we find the whole area, it's k pi over 2, and when we find the sum of the negative integrals, it's pi times k minus 1 over 2, and when we subtract the blue from the red, we get pi over 2, which is exactly what we wanted. So we can conclude that for any odd positive k, the area of the shaded region of r of theta equals sine k plus 1 theta over k will always be pi over 2. We'd like to give a special thanks to Dr. Philip Benj from NCSSM and Dr. Todd Lee from Elon University for their guidance, contributions, and support. And we'd also like to thank the North Carolina School of Science and Mathematics Summer Research and Innovation Program, the Bureau's Welcome Fund, and the NCSSM Foundation for making this program and research possible. Thanks for listening.